and welcome to all of you. Thank you for joining us in today's webinar, Debunking Science of Reading Neuroscience Claims. I am Dr. Edgar Lampkin, the CABE CEO, and this webinar is going to discuss with our speaker, hello and welcome to Debunking Science of Reading Neuroscience Claims. I am Dr. Edgar Lampkin, CABE CEO. Our speaker and group of panelists, the science of reading, which is a critical issue for CABE as it negatively impacts our English learners, emerging bilingual learners in education. Recent legislation has brought its methods and claims to question. This webinar is going to explore the controversies and shed light on the myths and realities of science of reading regarding the faulty neuroscience and linguistic claims. We invited Dr. Stephen Strauss to join us. We will also have, he will provide a critical analysis of the false neuroscience and linguistic claims promoted by science of reading. And we also have a panelist and insights on experts in our neuroscience, linguistic, and biliteracy. But before we get started, it gives me great pleasure to introduce to you CABE's Director of Program and Event, Delma Sheridan, who will give you some important information and direction about how today is going to flow. So Delma, I'll turn it over to you.
Thank you, Dr. Lampkin. Hello and welcome, everyone. We're glad you're joining in today's webinar. My name is Delma Sheridan, and I am the Director of Program and Event here at CABE. Today's webinar is presented by an impactful researcher and practitioner in the field of neuroscience and linguistics. As we get ready for today's exciting session on the science of reading, I have a few housekeeping matters to share with you. At this webinar, the speaker and panelist microphones will be active, and participant microphones will be muted. If you would like to pose a question during the presentation, please use the question and answer QR code you see right now. Put your phones near it and give the sheet, and you will be able to address, you will be able to present questions which will be addressed at a later date and available for viewing on the CABE website at gocabe.org on May 15th, 2024. We'll have it ready to go for you on that day. Now that you've received this information, I would like to return it back to our own CEO, Dr. Edgar Lampkin.
Thank you very much, Delma. And it gives me great pleasure now to share with you that we have two terrific moderators with us, panelists that are going to be asking questions. And so that is Dr. Barbara Flores, who is professor, literacy expert, has trained over 10,000 teachers, and so we're excited to have her and be able to moderate, ask questions, and engage with Stephen Strauss. We also have with us the other moderator, which is Dr. If we can switch the slide, we have Dr. Jill Kerper-Mora. She's an author, an advocate, a professor from San Diego State University. We're so excited and thankful to have her. She's also a literacy expert and has also been involved in training bilingual teachers. So without further ado, Dr. Barbara Flores, I'm going to turn it over to you so you can introduce our presenter and share with folks his background. Thank you.
Thank you so much, Dr. Lampkin. It is my honor to present Dr. Stephen Strauss, MD, PhD. He's board certified neurologist, and he was certified by the American Board of Psychiatry and Neurology in 1993. He is still a practicing neurologist. Some of his academic positions were Professor of Neurology, University of Maryland, Professor of Linguistics at the University of Vienna and Vienna Neurology Institute, Professor of Linguistics at Arizona State University and University of New Mexico. His educational training is in not just in neurology, in the Department of Neurology at the University of Maryland Medical Systems, Baltimore. He also was a student neurology rotation at Johns Hopkins Hospital. He did his internship at the University of Maryland Medical Systems in Baltimore. He was given the Fulbright Award for research and teaching on aphasia and linguistic theory, clinical neurology at the University of Vienna Neurology Institute. He got his medical degree at the University of New Mexico School of Medicine. Also has his PhD from in linguistics from the Graduate Center, University of New York Graduate Center in New York, and he got his undergraduate degree at Stony Brook State University of New York at Stony Brook in mathematics. Among his most prestigious awards are the following two. He got the John Dewey Award for Extraordinary Contributions in Education of Young People in America from the Vermont Society for the Study of Education. And of course, the Fulbright Award, prestigious Fulbright Award for research and teaching on aphasia and linguistic theory at the University of Vienna Neurology Institute. He has been a keynote speaker, and actually 3 years in a row, I was the keynote speaker at the Conference of Medicalization of Education in Brazil, Sao Paulo, Rio de Janeiro, and Salvador, Brazil. He was also a keynote speaker at the University of Cape Town in South Africa on the linguistics of phonics. He brings to us quite a resume and a very unique combination of neurology, neuroscience, and linguistics. I'll just share three of his major works: The Linguistics, Neurology, and Politics of Phonics, Silent A Speaks Out; Brain Research and Reading, How Emerging Concepts in Neuroscience Support a Meaning Construction View of the Reading Process, with Kenneth Goodman and E.J. Paulson. And lastly, Reading, The Grand Illusion, with Ken Goodman and Peter Fries, that was recently published in 2016. And without further ado, I'd like to introduce, give it back to, I'm going to, Jill, Dr. Mora, are you ready for the first question? Or does it go back to you, Edgar?
No, I think we're ready to roll. Let's ask the first question, Dr. Jill Kerper Mora.
Okay, would you bring that up, please, on the screen? First, Dr. Strauss, we would like to ask you about how your PhD in linguistics has informed your neuroscience research, and also vice versa, how your neuroscience research has influenced your understanding of linguistics.
Okay, let me get this started here. Can you hear me?
Yes.
Okay, but I see that my face is not on the screen, but if we can fix that. Oh, it is on the screen? Oh, okay. Well, first of all, let me thank everyone who invited me to this very wonderful and important event. Dr. Flores, who I've known for many, many decades. And if I know anything about bilingual education, it certainly is from her. Dr. Mora, and thank you very much for inviting me too. And Dr. Lampkin as well. I really appreciate it. And I appreciate the help from everyone else in CAVE for this opportunity. I have loved the brain my whole life. I remember when I was a little child telling my pediatrician that I wanted to be a brain doctor. I didn't know what I was getting myself into, but I did say that. I still love the brain, what it allows for us to be human beings. And my favorite part of the brain is the part or parts that have to do with human language. How did linguistics, or how does linguistics inform us about how we could address the neuroscience of language? Neuroscience means a lot of things, but today it refers to what we know about how the brain works, and more specifically, what we know about how the brain deals with human language. Many, many years ago, I guess a couple of 100 years ago, there were very early understandings of how the brain, or what the brain did with language. This was mainly from people who had strokes or traumatic brain injuries, followed by autopsies where we could see, or the neurologists at that time could see, what part of the brain was damaged and what the effect was. So they noticed that if the left side of the brain towards the back, that's called the posterior area, was damaged, patients who had damage there from a stroke or other problem could not understand well. That area was called Wernicke's area. And more forward or anteriorly in the brain, they noticed that if people had an abnormality there, they couldn't express themselves. So at least they were dealing with two pretty obvious components of language, and we certainly have learned a lot since then. Let's go to the next slide. So there's been obviously quite a bit of change in our understanding of linguistics and language since then, with revolutionary changes in linguistics beginning in the 1950s. We know that there are two different aspects of language that can be studied. One is time independent, and by that I mean it's not something that proceeds through time, it's simply knowledge of how the grammatical rules work, for example. But there are other aspects of language that proceed in real time. Reading, speaking, writing, listening, those occur through time, and that therefore allows us to address the question of how the brain functions in real time in order to accomplish those linguistic processes. What we would like to see in the brain, when we understand that certain aspects of language take place in real time, the ones that I mentioned, is how the electrical circuits in the brain move the electrical currents from one region to another and accomplish reading, accomplish writing, accomplish listening, and accomplish speaking. So let's go to the next slide. We've learned a lot about language itself. We've learned about sound structure, phonology, how texts are put together. We've learned about different aspects of multilingualism, word structure or morphology, syntax, semantics, and we have a lot more to work with given our linguistic knowledge today with respect to how we can investigate the brain. It's not simply understanding language and producing language, but how do we deal with individual words? How do we deal with sentences and so on? So let's move on. Okay, question 2.
Yes, question 2. Dr. Strauss, what are some of the problems using the MRI and other brain imaging techniques to study reading? What has been your research and experience?
Okay, that's a very good question, because MRIs are used today as one of the most important tools to study language according to the principles advocated by the so-called science of reading. I could say, based on the previous slide, that one of the big problems is you cannot put 3 people in the MRI machine, but we can do lots of studies with 1 person. The MRI machine is very limited. When we use machines that investigate real-time processes, there are what we always look for are what we call temporal resolution and spatial resolution. Spatial resolution means if we have 2 different events, somebody saying a sentence that is just an affirmative type of sentence, or somebody asking a question, can we see in the brain the separation of the areas of the brain where those two things are taking place? That is called spatial resolution. Sometimes two different events cannot be spatially resolved and they look like they're taking place in the same part of the brain. What SOR researchers try to do is experiments to see if they can separate two different linguistic events to two different parts of the brain. Temporal resolution is not very good with MRI machines. So what does this mean? It means that because the spatial resolution is very, very good, but that because the temporal resolution is not good and the events that are studied have to take place very quickly, the MRI machines are really limited to taking pictures of subjects reading very short pieces of language, syllables, single words, maybe a nonsense word, but it cannot study text. It cannot study what children and adults actually read. And therefore, the principles and discoveries they make, which they call studies of reading, are inherently limited by the MRI machine. It raises the question of whether the SOR, the science of reading advocates, are constrained to study the identification of individual words because that's all the MRI machines allow them to study. We need different kinds of methods to study the reading of natural language materials, real books, real poetry, real recipes, things of that nature. Those cannot be studied on an MRI machine because the temporal resolution is not good enough. Okay, let's move on again.
Dr. Strauss, can you also go back to the last slide? Because the last point about sounds and letters, is that also apply in terms of the limitations?
Oh, hello. Those are very short events, and the shorter the event, the better. Excuse me for my voice, I apologize. So identifying a letter or a syllable or a word, those can be studied because they're very quick. The SOR advocates are trying to study the quickest events that they can because those are the events that are most readily analyzable by these MRI machines. I hope that answers your question.
Yes, thank you.
All right. So another limitation, and I'll be brief on this, is that the way the MRI works in the study of reading is that the reader is given a task to do. For example, you're given a word to look at, and you have to sound out the word or read it out loud. And then the blood flows to that area of the brain where the event is taking place. So the researchers look for where the blood is going, and what they would like to say is, well, that's where this event occurred. Except they can't do that because the blood is also going to other parts of the brain that have nothing to do with reading. For example, it goes to the parts of the brain that keep you awake. It goes to parts of the brain that allow you to sit up in your chair while you're reading and not topple over. So they have to figure out a way how to get rid of that stuff and how they can see only the part of the brain that sounded out the word. In order to do this, they have to have another task, which is very similar to the first task, which has the same level of attention. You're sitting on the chair the same way, you're not sleeping the same way, and so on. And they then take a picture of that and subtract one from the other. So they subtract out all of the blood that goes for your sitting posture and everything else. And they need two very, very similar tasks in order to accomplish that. So if they want to know where does a reader read a phonologically transparent word, they have to subtract from that something which they think is pretty close, and they will use a pseudo word, something like, plugin, which doesn't mean anything, but it can be sounded out. And in that sense, the only difference is that it's not a word, but it can still be sounded out. They subtract the picture of blood from one MRI from the other MRI, and they claim that they have now seen the difference. So when they tell you that this is where words are sounded out in the brain, which is on the left side in the back, what they're really saying is this is where the brain distinguishes sounding out words from sounding out non-words. And that should be kept in mind. Because, who has a theory of reading that says that readers have to know how to sound out non-words? Okay, next slide. When they do these kinds of studies, they look at readers who they think are typical readers. These are readers who basically can sound out words. They look at the letters, they know the sound that corresponds to them, and they can do it. They define dyslexic readers as readers who can't do it. And what they find is what you see here on the slide, that dyslexic readers, what you see in this picture of the brain, the left side is the front of the brain, the right side is the rear of the brain, and we're looking at the left side of the brain. The left hemisphere, the left side of the brain, is what predominantly controls language. So you can see that in the dyslexic readers, nothing lights up in the rear part of the brain. And additional studies by the science of reading researchers have shown that the rear left side of the brain is where words are sounded out when they are given in isolation to a reader. So I hope that's clear. Let's go to the next slide. Okay, Sally Shaywitz, pediatrician at Yale School of Medicine, studied dyslexic and non-dyslexic children. Defined by the child simply not being able to sound out words. There are other criteria which she never follows. I can discuss that in one of your questions if you'd like. In other words, she violates her own criteria when she submits these studies for publication. But in any case, she gives the dyslexic readers lessons over a number of weeks on how to sound out words. She repeats the MRI, and lo and behold, she finds that their MRI now looks like that which we see in typical good readers, that it's not missing the rear components, which you saw on the previous slide. Her conclusion in a very well-known article was that she was able to repair the brains of these kids. There was something wrong with the brain, and she repaired it. The editors of the journal that she published this article said, wait a minute, all you showed was that you taught the kids something and they learned what they were taught. She never showed that she repaired anything. She never showed that what the task was that she gave them had anything to do with reading. She simply gave them a task, and the MRI was able to perform what certainly could have been and is really a completely meaningless task. Okay, next. I might point out that Sally Shaywitz also was someone in the SOR community who suggested that educators who do not use this science of reading should be charged with educational malpractice, just as physicians who don't do the right thing should be charged with medical malpractice. Right away, we see that there's something political about this. Okay, next slide. Okay, so with this methodology of giving readers very small specific tasks to perform, associating letters with sounds, putting the sounds together to make a word, finding the meaning of the single word, because remember, this is really all the MRI machine can do. They have found that different languages seem to be represented in the brain in slightly different ways. And they attribute that to the different kinds of alphabets that they have, the different kinds of letter-sound correspondences, the different kinds of grammatical structures, and so on. And you can see in these pictures, the left column is the left side of the brain, and the right column is the right side of the brain, that there are some differences. You can see the green areas are a little different, so are the blue areas, and so on. So they claim there are some differences, which is probably true. When I was in Vienna studying language difficulties in people who had strokes, we studied one man who had a stroke. He grew up fluent in 5 languages, and when he had the stroke, the effect that that stroke had on the 5 languages was entirely different from one to another, which means that those languages had to be in slightly different places in the brain. The brain accommodated all 5 languages by putting them slightly in different locations. Okay, next. Is the science of reading someone was going to read it?
Yes. And I want to tell you that I am bilingual because of Dr. Wilder Penfield's concept of the committed cortex that you just explained. So this is a very personal matter for me. So tell us, Dr. Strauss, is the science of reading a science? And is it a science about reading?
Okay, let's go to the next slide, and I'll say in one sentence what's on that slide. The science of reading is a science, but it is not about reading. It's a science of basically what MRI machines are capable of doing. Basically, we can ask, we built this machine, physicists and engineers who are really smart knew what they were doing. This machine can take pictures of the brain when somebody is performing a certain task. Let's see what the limits are of the MRI machine. Let's give it some completely meaningless task, like identifying an upside-down H. Can we find a part of the brain that is able to accomplish this? And lo and behold, the MRI machine can. Does that mean that being able to identify an upside-down H, which is really the same thing as a non-upside-down H, so let's pick a different letter, R, does that mean that being able to identify an upside-down R has anything to do with the theory of reading? Or is it just a meaningless task that uses letters from the alphabet? If we can show that this is just a meaningless task, meaningless from the point of view of reading, then the science of reading is a science, but it's not a science of reading. It's simply a science of MRI machines. What are MRI machines capable of doing? What are they not capable of doing? And that's one of the major, if not the major flaws of the science of reading, because they rely on MRI and other technology to identify small pieces of language. Okay, let's go to the next one. They also use, just with regards to whether they're studying reading, this is the model of reading that they have. First of all, you should keep in mind that their understanding of reading is that it is the process of identifying individual words. You identify one word at a time. They have 2 different routes to getting at the identity of a word, because they recognize that some words of English can be sounded out easily. They seem to follow all the regular rules, but other words cannot. We all know those kinds of words, sign, S-I-G-N, and so forth. So they postulate 2 different routes. One is non-lexical, that's the sounding out. The other is lexical. And they look for the parts of the brain that carry out these 2 different pathways to identifying a word. They never point out that this model of reading is 100 years old. It goes back to the behaviorists in the United States, mainly Leonard Bloomfield, and it was completely discredited, about 75 years ago. I'll talk to you about why it was discredited. Let's go to the next slide. One of the things that really upsets these people, these advocates of the science of reading, is that there are languages where the spelling of words are not readily connected to their sounds. English is a well-known example. There are so many exceptions to the phonics rules. Italian, on the other hand, really has hardly any, if any at all, exceptions to their phonics rules. And there are languages which lie in between. So Spanish is pretty close to Italian, German has 50-50, and so on. And what they found in studying what they call errors, which simply means the child did not sound out the word correctly, that's their error. What they found out was that the more transparent the written language is, and it's quite transparent in Italian and not transparent in English, the less transparent, the closer it is to English, the more errors were made by the reader. And all that means, remember, is that the more times they did not sound out the word correctly. So let's look at the next slide. They get bent out of shape over this. Dahan, a well-known person in this field, calls this the abominable irregularity of English spelling, and says that because of this we need spelling reform. We should spell the sound F with one letter, F, and not with PH, and then life would be a lot simpler. Let's go to the next slide. I'm going to talk about this more when we get to the alphabetic writing system of English and other languages. Okay, the theory of reading that these people use, as I said, is 100 years old. And they call themselves the scientists of reading, but truthfully and truly, I mean, they really have not demonstrated their investigation of these assumptions that words must be sounded out individually before you can get to the meaning of the words. You have to identify them on the basis of their sounds, and then the sounds can lead you to the identity of the word, and then knowing the word can get to the meaning. There is empirical evidence for why this is not the correct theory of reading. They would like to say that whole language or other transformational socio-psycholinguistic models of reading, where readers use their background knowledge, their knowledge of how society works, their knowledge of semantics and culture and meanings to construct meaning. They would like to say that that's just a touchy-feely kind of approach to reading, and that advocates of that approach to reading do not have empirical evidence on their side. Well, the truth is they never even investigated that. But that approach to the science of reading has found very strong empirical, factual evidence that reading cannot be a process in which you first identify words and then later on can discover or locate their meanings. First of all, good readers do not even focus on 1/3 of the words on a page. And many of those are not seen. Just because they're not focused on doesn't mean you don't see them. They just are not in good focus, and many of those are not seen at all. So how does the reader know what they are? We know that good readers know what they are because they can tell us what the page meant. Think about a sentence that ends a page like, the dog wagged its, and then the next word is on the next page. You haven't seen it yet. Are you really going to say that? Oh, thank you for doing that. Are you really going to say that you don't know what the next word is after you've just read the dog wagged its? I mean, of course you know that it's tail. And you don't even therefore need to look at the next word on the page. You don't need to sound it out. At worst, you need to look at the first letter to confirm your prediction. And if you find out later that it was wrong, that the dog wagged its tongue, something will trigger that in your reading when you try to make sense of the print, and you'll go back and correct. And how do we know this? We know it because that's what good readers do. That's what readers who understand do. They make predictions. They may look at a letter, maybe not, to confirm or disconfirm the prediction. We see that they go back. When we ask them to read aloud, they do that. And this is the process of making predictions. Okay, let's go to so what you see on this slide is simply the foveal region, which is the letters that are in focus. The parafoveal region, the neighbors to the fovea, are less in focus and the peripheral vision is hardly in focus, and yet the readers can say them out loud because they make very good predictions. Okay, next slide. Here's what someone said about what how you can possibly read quickly if you don't even see so many words.
Hey, I'm being cited.
Basically what I said, that we are good at doing that because we make good predictions. That is to say, if we're reading for meaning and not reading to sound out letters. Okay, next one. And here you can see a real example of eye movements during reading. A fixation is when you stop and focus on the word. A saccade is when you move your eyes quickly to get to the next focus. The purple areas are words that are focused on. And look at all the words that are not focused on. At, Mr., the. Well, even if an SOR advocate said, well, you do sound out those words, but you simply don't say them out loud, they cannot explain why the pieces of language which you which you sound out but don't say, are a certain representative class. They're the small grammatical words of the language. The, Mr. apparently is one of them. They have no explanation for this. All of this is empirical evidence that their theory of reading, which is that without any background knowledge, without any cultural knowledge, without recruiting meanings that you already have discovered, you simply sound out one word at a time, you put them together, you construct meanings that way. All of this is scientific evidence that their so-called science is simply incorrect. Okay, next slide. I would just like to say, Newtonian physics studied large masses, objects that you could see, and they discovered what velocity is, acceleration, momentum, things like that. When quantum physicists studied subatomic particles, they discovered that Newton's laws simply did not apply. They had to come up with completely new laws of physics. The scientific field of reading has a history which is exactly the same. Initially, 100 years ago, the scientists of reading studied only individual words. The SOR advocates are still doing the same thing. But Ken Goodman was the genius who discovered that if you look at a larger text, if you don't restrict yourself to the minimal pieces of language, you discover that the laws of reading are entirely different. This is what the SOR advocates they simply don't understand that. Okay, next. Okay.
Okay, thank you, Dr. Strauss, for explanation. The next question is, does the science of reading accurately represent how the English spelling system really works?
Okay, next slide. I'm going to go through this briefly because I could spend weeks and weeks going over this because I love spelling and spelling rules in English. What the SOR advocates do not understand is that English is simply not an alphabetic system. There are so many exceptions, as all of you know. As I pointed out earlier, they don't like that there are exceptions. It's bad for their theory. You can't sound out words easily. What they never ask is, why does English tolerate all these exceptions? Why didn't it simply get rid of them? Well, we can look to other languages like Chinese, which you see on the bottom here, for a little bit of an insight into this. You see two Chinese characters. The first one means village. The second one means root. They are not connected semantically. When a Chinese writer wants to write out the name of the U.S. President Reagan, they take what in their language is something called a logographic character, a character that does not stand for a sound, but it stands for a whole word. The first one standing for village and the second one standing for root. And they take the sounds of those, the pronunciations of those two words, Li and Gen, and they get Ligen, which is Reagan in Chinese pronunciation. They use the logographic characters in an alphabetic way. Well, when English has beat and beat, spelled differently, and they mean different things, or hull and haul, and sane and sanity, and so on. What it is conveying, despite the fact that the spellings are different, even though they have the same pronunciations, is that they are different words. Now, what does that mean? That means that English is an alphabetic writing system. It uses alphabetic letters, which do stand for sounds, but they are now being used in a logographic way. They're being used to distinguish one word from another, just like the logographic system in Chinese is used at times to convey sounds. These languages are hybrids. That's an interesting discovery about writing systems, that there are hybrids of logographic and alphabetic systems, and the logographic part of the English spellings or English writing systems is something that the science of reading advocates simply cannot explain, and it goes against their entire thinking, but that is how English writing works. I think we can skip the next slide for the sake of time. We can skip this one. I was going to have a whole big spiel about the silent E, but we'll do that for another time.
Dr. Strauss, I think you should deal with it. We have time.
I do have time?
Yes.
Oh, okay, so go back to silent E. Okay, silent E supposedly makes the preceding vowel long. Well, here are cases where it does or doesn't. Race, rice, reese, yes. Rage, hide, tote, mute, yes. Tense, sense, rinse, no. Marge, large, barge, no. If they were with the long vowels, we'd have teens, seens, rinds, marriage, large, and bears. But obviously we don't pronounce it. Well, does silent E really make the preceding vowel long? First of all, we see two lines where that's not true. And the third and fourth lines, we can ask, are they exceptions? Are they different from the first two lines, or do they all have something in common? Well, they all have something in common. If you remove the letter E from the first line, you will get the word tens, you will get the word sens, or the non-word sens, and rins. If you remove the E from the second line, you get marg, larg, and barg. If you remove it from the third line, you get rack, rick, and reek. And from the fourth line, you get rag, hid, tot, and mutt. Well, what you're getting in these cases, let's say the first three lines for sure, is that E prevents a preceding letter from being sounded out a certain way. E itself is never sounded out, but it has an alphabetic function that is complex. It's not a one-to-one phenomenon. And in fact, it does not even make the preceding vowel long. What you can see is that it prevents the preceding vowel from being short. When we look at race, rice, and reese, the preceding vowels are A, pronounced A, I, pronounced I, and E, pronounced E. The long vowels are the default vowels. The letter E at the end, the silent E, prevents the default vowels, A, I, and E, from turning into their short or non-default vowels. So the function of silent E, which is not sounded out, is to influence the pronunciation of preceding letters. Without it, those letters would be pronounced differently. That's very different from saying that each letter has its own pronunciation. In this case, the letter pronunciation is influenced by another letter later in the word. Dahan, in his book, he's regarded as one of the premier SOR scientists. He says that you read a word from left to right, one letter at a time. Well, that's impossible with these words, because then you would say tens, e, and then E, and then you'd have to drop the E and turn the Z in tens into S. It goes against their own theory. Okay, I hope that was clear. Let's go to the next one.
Well, Dr. Strauss, I am so glad to hear the silent E speaking out. Tell me about the all of the activity that's going on in the brain during meaning making. because you've shown us all of those different parts of the brain, and somehow the brain has to coordinate the information. So would you explain that process?
Okay. Well, to explain that process, I think we we will benefit by looking at the next question. But as a preliminary answer, I could just point out the way the science of reading scientists deal with this and the way others deal with it. The science of reading advocates or scientists start, as I said, with the identification of individual words. This begins in the rear part of the brain, what's called the occipital lobe, where the visual form of a word is obtained, because the occipital lobe is the lobe responsible for seeing things. So the visual information of the word on the page goes to the occipital lobe. Then the electrical current moves from the occipital lobe more forward in the brain, according to these people. It goes to a part of the brain that is closer to sound, where we hear things. That's more in the left temporal region. That's forward from the occipital lobe. So the visual form of a word and then the identification of the letter components is turned into sound. The sounds lead to, well, the lexicon of the language, which is where words are identified, and then the words are connected to meanings, and all the meanings of individual words are put together to form a whole text meaning. Professor DeHaan says that at that stage, we have absolutely no idea how the brain does it. We do have some idea, though. The reason they give for why visual words, in other words, the letters, let's say, the letters visually have to be turned into sounds, is because they regard written language, visual language, as unnatural. It appeared late in human history. Spoken language, oral language, they regard as natural. It's already in the brain. The brain is genetically wired to have spoken language. And because written language is not natural, you have to turn that form of language into spoken language before you can understand anything. Well, anyone who uses sign language will tell you that that's not correct, and there are many arguments against that. So let me proceed with the next slide, because I think it will answer the question a little better. I want to focus your attention on the blue circle down in the middle of the brain there, which is called the thalamus. The thalamus it's my favorite part of the brain. I didn't know it existed before I went to medical school, but when I was taught about it, I fell in love. The thalamus collects information from the outside world, visual information, auditory information, and then it sends it to the outer parts of the brain, the lines that you see called the cortex. The cortex puts that information together and creates meaning. So if you go to the next slide, you'll see that what I've written here is that there are nerve cells, which are called neurons, that go from the thalamus to the cortex. The cortex is the outer part of the brain, and the frontal cortex, the cortex in the front of the brain, is the most evolutionarily advanced piece of brain that exists. It's what allows us to think, to plan, to decipher things, to what's called the executive functioning, where we can predict things and so on. There are pathways that go from the thalamus to that cortex. And the very traditional view of the brain is that the way the cortex constructs meaning is by getting information from the thalamus, which itself got information from the outside world, putting all those pieces of information together, and then lo and behold, you have meaning. There are also nerve cells, nerve fibers that send electricity from the cortex, from the executive functioning part of the brain, back to the thalamus. And recent researchers have said there is a revolution going on in neuroscience, which is entirely different from what the science of reading people, advocates are insisting on. They want to, and they do insist on the thalamocortical pathways, the pathways that bring information from the outside world up to the cortex so that you can then understand what you're looking at. The corticothalamic pathways and the scientists who have discovered these point out that, well, you know what? There are actually 10 times as many nerve fibers going from the cortex to the thalamus as there are going from the thalamus to the cortex. Therefore, those fibers going from the cortex, from the executive part of the brain, the part that predicts and plans and so on, to the thalamus, those must be more important. Prediction is more important in how the brain works than gathering information to discover meaning. The brain makes a prediction about meaning, and then it asks the thalamus, am I right or am I wrong? And then the thalamus looks for certain visual information. Is it red? I'm looking for my red car. Well, let me look for red, because the thalamus deals with visual information. If it finds red, the prediction is confirmed. If it doesn't, the prediction is, what you're looking for is not confirmed. The same thing goes with letters and sounds. So these scientists have pointed out that the brain, if we want to understand the brain fully, we need to recognize that the essential functioning of the brain is to create meanings, and creating meanings is simply a matter of making predictions. And we use the thalamus, the deep part of the brain, not simply to send stimuli to the cortex, but to confirm or disconfirm the predictions that the cortex is making. The truth is that the electrical currents go back and forth. You make predictions, you confirm them, then you make, or disconfirm them, you make other predictions. It's a dialectical process. But the point is that there is now a real theory of how the brain works, which explains in terms of neural pathways how the brain does exactly what the socio-psycholinguistic approach to reading says it does. It first predicts meanings and then confirms or disconfirms them. So let's go to the next slide. Why is it political? And we have just enough time. Okay, this is more than just a scientific matter, as all of you know, and which is something that makes me happy to talk to all of you about this, and something which I hope all of you will have questions and responses to, because this is a political matter. You know about the legislation that has been, well, defeated, but will certainly rear its head again in California and in so many other states, to mandate that the science of reading be instituted in classrooms. Let's move to the next slide. First, we can ask, how do we even know right away, right off the bat, that the science of reading is political? Well, first of all, mandates created by state legislatures only apply to public schools. Private schools can use them, but they're not forced to. How come they only apply to public schools? If all schools, including private schools, are mandated to vaccinate children, and if the science of reading model is so serious that Dr. Shaywitz says that teachers and educators should be charged with educational malpractice if they don't do it, why don't they mandate it for private schools as well? There's a difference between students in public schools and students in private schools. Another way that we know for sure that there's something political about this is if you look at the names of committees, government and lobbying committees that deal with reading and education. If you look up the names of the House and Senate committees that deal with education, they don't say the Committee on Education. They are called the Committees on Education and the Workforce, Committees on Education and the Labor Force. These people will see public education as a factory to produce certain kinds of workers. ALEC, which writes the laws that they then give to the politicians to pass, also refers to its educational task force as a workforce development, the Committee on Education and the Workforce, and the Business Roundtable, the biggest corporations in the country, back in the 1990s, referred to public schools as workforce development systems. This is rather curious because they don't see schools the way teachers see schools, especially public schools. They see schools as arenas where they can mold kids into the types of workers that they feel are needed in the new economy. Teachers see schools as places where children can develop, discover who they are, discover their own interests, their own likes and dislikes, what is important to them, their social relationships. That's very different from simply turning schools into workforce development systems. If you skip a couple of slides and go to the last one, the next one, the one before that, yeah. Everybody's familiar with STEM. This was actually promoted by President Obama with millions of dollars. In line with this, science, technology, engineering, and math, that's the workforce that they want to create. They need to be able to force the schools to do something. They can easily do it with the phonics approach to reading. Why is that? Because you can test kids on it. You can say whether the approach is working or not. If the kids are not doing well on the phonics tests, you can take over the schools. You can fire teachers. You can mold it to whatever way you want. You cannot test a kid on how they interpreted a book that they really like. You cannot test a kid on what kinds of books they like to read. Those kinds of things which teachers understand are important are simply not testable. The science of reading approach is testable in the schools. So as opposed to STEM, I've come up with what I think is a better curriculum for public schools. I call it PALM, physical education, art, learning languages, and music. And I think that teachers should advocate for this. You cannot have this unless you have democratic classrooms, kids choosing what languages they want to learn, what music they want to listen to, what books they want to read. You can't test a kid with this, and that for that reason, there is not a strong imposition from the outside governmental authorities. These classrooms are democratic, and it would certainly be in line with what professional teachers understand teaching is all about. I think that it's not a coincidence that the science of reading people have a theory which fits right into MRI machines, which cannot study longer pieces of language like texts, and which fit very easily into a school system that tests kids to death. We need to turn that around. I think that it's one thing to have the theory and the science on our side, but I also think it's pretty obvious that they could care less. The politicians really are not swayed by that. They will be swayed if we all can reach parents and students who will then protest in great numbers. The politicians will be scared of them. So far, they don't seem to be scared of us. We have a lot of work to do, and I hope that I've been able to help out with that struggle, which we all need to be involved in. So I thank you very, very much.